Hi everyone, today we're going to talk about molar enthalpy of reaction. This is tied to learning objective of College Board that we can use calculation to estimate energy changes, and then we can design and interpret an experiment in which calorimetry is used to determine change in enthalpy. Now we're going to try a series of problems today. One is the molar enthalpy change of dissolution. A student performs an experiment to determine molar enthalpy of solution of ammonium nitrate when mixing 2.5 grams of it with 95 grams of water. The temperature data is shown in the graph below. Notice that initial temperature was 25 degrees C, and finally it was 22.9 degrees C. Temperature went down. Determine the change in temperature. Is the reaction endo or exothermic? Assuming no heat loss to the calorimeter and specific capacity is 4.18, calculate enthalpy change for the dissolving of ammonium nitrate in kilojoule per mole. From the graph, we can then calculate the delta T, which is 22.9 minus 25 degrees C or negative 2.1 degrees C. The reaction is endothermic because the temperature of the solution went down. The heat is transferred from the surrounding to the system as ammonium nitrate dissolves. The mass of the solution is the water, 95 grams, plus 2.5 grams of ammonium nitrate, the solute, to make up a total of 97.5 grams. The Q is calculated as ms delta T with a negative value of 856 joule. That representing heat released by the solution and absorbed by ammonium nitrate. So the Q is representing the heat energy of the solution. Now in 2.5 grams of ammonium nitrate, it contains 0.0312 mole if we divide it by the molar mass. Therefore, the enthalpy change of the reaction is minus Q of the solution per mole, which becomes 27.4 kilojoule per mole. So the negative of a negative will generate a positive. Remember, enthalpy change is that of the system for the reactant. And the Q is for the solution. Therefore, they are opposite in sign. Practice problem number 2, molar enthalpy change of neutralization. If 1 molar of KOH are mixed with 1 molar of sulfuric acid using different volumes, and the temperature changes are recorded, total volume being kept constant at 120 ml with the following graph. Now notice that on the y-axis we have temperature, on the x-axis we have volume of KOH increasing from 0 to 120 ml, while we have the volume of sulfuric acid decreasing from 120 to 0 ml. This is called a method of continuous variation. So for all the data of temperature obtained, we then plot two lines of best fit and let them intersect at a point which is equal to 80 ml of KOH mixed with 40 ml of sulfuric acid. Determine the volume which produced the highest increase in temperature. Write the net ion equation for the neutralization and calculate Q, and determine enthalpy change of neutralization per mole of KOH. Is it endo or exothermic? I said earlier that the maximum point of temperature is where the two lines intersect at 40 ml of sulfuric acid and 80 ml of KOH. Now the moles of sulfuric acid, taking 1 molar and 40 milliliters, is calculated at 0.040 mole, and the moles of KOH in a similar fashion is calculated as 0.080 mole. Therefore, the mole ratio between sulfuric acid and KOH is 1 to 2. And we write the net ion equation as 2 moles of hydrogen ion to combine with 2 moles of hydroxide ion to make 2 moles of water. Now the mole ratio is 1 to 2 because the 2 moles of hydrogen ion comes from 1 mole of H2SO4, and the 2 moles of hydroxide ion comes from 2 moles of KOH. Calculating Q, it is equal to 120 grams, because we have 120 ml with a density of 1 gram per ml like that of water, times specific heat of water 4.18, times the temperature change, which is 33.5 minus 25. And we have 4,300 joule of heat. And dividing that by mole and change the sign to convert into enthalpy of the reaction, we have negative 54 kilojoule per mole of KOH. The reaction is exothermic because temperature in the solution increases. Practice problem number 3. Now we have a single displacement reaction. Find the molar enthalpy change. And the student is mixing 6 grams of excess zinc metal with 25 ml of 1 molar copper sulfate solution in a coffee cup. The following graph is obtained. It is very important we know how to extrapolate data from the graph. We started with 26 degrees C of temperature in the coffee cup, and we add the zinc. The temperature went up initially, and then it gradually tailed off. To obtain the maximum temperature, we then extrapolate the line as in a diagram, and then calculate this delta T, starting with 26, writing a vertical line up where we cut the dotted line. We need to write a net ionic equation for the reaction. Is it endo or exothermic? Calculate the molar enthalpy change of the reaction assuming density is 1 gram per cubic centimeter, having specific heat of water. Calculate percent error if the theoretical value is negative 217 kilojoule per mole, and talk about a major source of error. How would the enthalpy change value be changed if the pipette using to measure the copper sulfate solution was wet with water to begin with? So here's the net ionic equation. Zinc metal, we're acting with copper 2 plus ion in aqueous solution to form zinc 2 plus ion in aqueous solution and copper metal. Now the reaction is exothermic because the temperature changed from 26.0 to 65.5 as extrapolated on the graph, which I have discussed earlier. Therefore, the delta T is 39.5 degrees C. Now, in 25 milliliter of copper sulfate, using density of water, we have 25 grams of copper sulfate. This is added to the mass of zinc. We have a total of 31 grams in the solution. Calculating Q, we have 5,120 joules. Regarding the moles of copper sulfate, which is limiting, it's 1 molar times 25 milliliter, or 0.025 moles. Now, taking the Q and change the sign, and divided by the moles, we have enthalpy change of the reaction, and we have received negative 205 kilojoule per mole. The percent error then compared to the negative 217 kilojoule theoretical value is calculated as 5.53%, and we actually have a lower value than the theoretical value. The major source of error could be heat loss to the calorimeter and the surrounding air. That means heat has been absorbed by the calorimeter and the air, leading to a lower or smaller enthalpy change calculated. If our pipette delivering the copper sulfate solution was wet with water to begin with, that means the copper sulfate solution would have been diluted by the water, resulting in smaller moles of copper sulfate reacted or delivered, and then yielding a smaller, lower temperature change and a lower enthalpy value calculated. Summarizing what we have learned today, we learned how to use the technique of calorimetry to determine heat transferred. We calculate molar enthalpy of reaction and from data and graphical representation, such as in dissolving, in neutralization, and in single displacement reactions. Finally, we analyze for sources of error in calorimetry labs. I hope that you have found this video helpful. If you like it, please give us a like, and I look forward to seeing you again in the next video.